UWE joint program and had positions at UC Berkeley and UConn before arriving at UC Santa Cruz as a faculty member. His research focuses on development and analysis of regional ocean models and using these to study ocean circulation and interactions with biogeochemistry and fisheries. His research presently focuses primarily on physical and biological interactions within the California current system, which is what he'll be talking about today. So let's welcome Chris.
Thanks very much. It's a real pleasure to be down here. It's such a gorgeous facility, and I appreciate also the intense spirit that I always perceive when I come to Moss Landing. I sort of sense it by talking to people, the excitement that is always here, and it's really nice to see. So today I'd like to talk about some modeling and assimilation type ideas. The talk is going to be divided into two parts, and the first part is kind of process oriented, and the second part gets more to the details of assimilation type of modeling that I do. And so I'm going to highlight Jason Jacobson, who just graduated from my group back in December and is now up at Oregon State. That's the first part. And then I'm highlighting Paul Matern, who's been came as a postdoc and has been a research scientist working with me for a number of years. We worked together on the assimilation parts. So there are many more people who have contributed, including Clark, in really important ways. But I just wanted to point out really my gratitude for everyone who I'm working with. Different parts of this are funded by lots of different projects, and I'm grateful for all of those sources of support. All right. I'm going to start with internal wave generation and its impact on primary production. And this is work that Jason Jacobson did. This is a nice movie. I put it in because I thought Dustin might be here, but he's not. Anyway, it's a nice animation of a global simulation using the Darwin biogeochemical model by colleagues. This is the same model that I think Dustin is working on. It was developed originally by Mick Follows in 2007, and it's just an example of a very complex biogeochemical model. We have some collaborations with the MIT group looking at the Darwin biogeochemical model, both in the California current and in other regions, including Hawaii, which I'll get to in a moment. But it's really these simulations that motivated this work. So here are some simulations from the Hawaiian Islands. This is a Darwin simulation with 6 phytoplankton groups and 4 zooplankton groups. It's being done by colleagues at the University of Hawaii, Brian Powell and Tobias Friedrich. And it's just, so this is using the regional model, not the global model that I was showing in the last slide. And it's showing a cross-section across the Hawaiian Islands here at very high resolution. And this is an area that's well known locally. It's a site of, as I'll talk about later, previous observational programs. But what you see is along this pathway of the Hawaiian Islands is an elevated ridge system. And across that ridge system are tides which go back and forth. And there's a very shallow ridge going across the region between Oahu and Kauai. And if you look at a cross-section, in this simulation of multiple phytoplankton, this is showing the sum of phytoplankton as a function of distance, transect distance, and time. And what you can see clearly is there's a subsurface maximum, and there is kind of counter-propagating wave-like motion that's subsurface. We were curious about the generation, or what might be stimulating this production here. If you notice its highest amplitude in the vicinity of the generation region, this is this is above the ridge, and it weakens as we move away from the ridge. Anyway, you can clearly see the tidal motion going back and forth. So this led us to think about internal waves, which, how many of you have studied internal waves? A few? Have you heard of internal waves? So internal waves are like the coolest thing in physical oceanography after kind of the general circulation and sphere grip theory and, okay, coastal upwelling. Anyway, it's really exciting, and it's a really remarkable, oh, I guess I'll stop that for a moment, sorry. It's a really remarkable feature. It's different from surface gravity waves, which we're very familiar with, and it's different from sound and light as well, because these waves have group velocities that propagate and that move in one direction, and the phase velocity, the direction that the crests and troughs move, is perpendicular to that. It's really unusual. So that's what's shown in this left figure, and these are some beautiful simulations that were, well, these are some beautiful laboratory experiments, I think done in the 80s or so, with very careful light focusing by the density field. So anyway, what you see here is some sort of oscillator within a well-lit column of stratified water. And what you'll see is that the energy propagates away from the source. It moves in diagonal paths, but the crests and troughs will be propagating perpendicular to those. And anyway, that's what you can see on the right. This is like not even a model, it's the real thing. And it's kind of a classic demonstration of these really unusual features. So this is what we think is happening at the Hawaiian Islands ridge region. Instead of having a paddle, we've got tides that are moving across this ridge. And there are some interesting things when you get tidal motion past a ridge. Depending on the slope that's there, you can get some very intense beams, like was shown in that previous slide. When you have a subcritical slope, when you have a slope that's not, let's say, at this particular angle, you get an intensification of tidal energy in some region. But when you have this critical slope, you get superposition of the energy into a narrow beam. And anyway, the Hawaiian Ridge has some slopes that are very near critical, and so we think that you end up generating these beams, which you can model as well. So this now I'm going to flip from a sort of a schematic or a realistic configuration to a model configuration. We use the regional ocean modeling system, and we basically have a step function in the topography. Jason started actually with a ridge, but it was complicated enough that we said, no, let's just do half a ridge. Let's just do a step, because you ended up getting things moving in both directions. Anyway, it's forced by tidal motion, so it's a body force that extends through the fluid. It goes back and forth over this step bathymetry. And what I'm showing here is the average kinetic energy after several tidal cycles. So these are, the motion generates internal waves which propagate at a specified angle. That angle depends on the frequency of oscillation and on the stratification. This idealized problem has linear stratification, and so the angle is constant from the generation region up, and you can see it reflects at the surface, reflects at the bottom, reflects at the surface, and so on downstream. We were interested less in the internal wave aspect about it as on the biogeochemical impacts of it. And so instead of using a Darwin model, which is honestly very complex and more complex than we needed, we took the simplest model we could come up with. This is a well-known model that Peter Franks developed in the 80s, just an NPZD model. Anyway, it's like other models with nitrogen as a currency, and we set it up with profiles that basically started with a phytoplankton subsurface maximum, a nutrient profile that had some nutrient deplete region like you find in oligotrophic gyres, plus some nutricline starting down around 75 meters or so, and ran it to steady state just in a one-dimensional context. N, P, Z, and D ended up with these profiles, so sort of an amplification around 75 meters, but otherwise steady state. All right. What was cool about this is that we immediately saw a response. If you look at the primary production, so that's modeled in the NPZ model in the following way. You've got a maximum growth rate and then a Michaelis-Menten function that's based on the nutrients, and then a light function, which is an exponential decay with an exponential coefficient kx. And if you just do some sort of averaging of the phytoplankton normalized primary production, you quickly see that in the vicinity of these beams, you get a very substantially enhanced primary production at each of the areas where it's bouncing. So if we compare, for example, the primary production outside of the beams, one of these is the reference, the other one is underneath this star, and then within the beams you get a substantial increase and a shift to higher latitude, higher elevations. All right, so the goal was to understand what might be causing this. There are a couple of possibilities. One of them is a light impact. So if you think about wave motion, you have some sort of circular or oblong pathway that it takes, and if you sit it in a nonlinear light field, so if you simply oscillate something vertically in a nonlinear function and it's linearly dependent on that light function, you're going to spend more time in much higher light levels on the upswing than you will on the downswing. So if you integrate the exponential light function, the amount of production happening on its upper half is quite a bit larger than that loss during the lower half. And we did some Lagrangian calculations to show that, in fact, these things do have substantial vertical orbits. And so this was one serious possibility. This was our initial hypothesis. Possibility two is that it's nutrient changes to the nutrient function. So I'll just, let's see, I'll say that we ran this with a passive tracer that was resembling the nutrient in order to get rid of biological production. And what we found was in the vicinity of the beams, you found an elevated nutricline, basically. You can see the bump. It's more substantial at depth, but you can see it up in the top probably most clearly here. And associated with that is also, you can see a significant enhancement in the nutrient anomaly. Anyway, so these two possibilities existed. And if you looked at basically the nutrient factor or the light factor, you could show that the light factor was not very predictive of the elevated primary production under a number of different conditions with a number of different topographic structures. You could see that you did have large elevated primary production with large light factor, but the linear relationship was very poor. In contrast, the nutrient factor was extremely predictive of the elevated primary production under a variety of different step conditions. And so, so that's what we realized was happening. A different way to analyze that was to look at the advective flux divergence in the model. So just briefly, the advective flux divergence is what's responsible for a time rate of change of a nutrient, or any other tracer. So ignoring mixing, which we examined and was found to be very, very small, the time rate of change of nitrate in this case, plus an advective flux divergence is equal to 0. So you can basically say that any time rate of change is just equal to the minus divergence of the nitrate flux. And that's what's shown over on the right, where in the vicinity of the beams in shallow water, you get an enhancement of the nutrient field right in the midst of these beams. That's shown up here in the net tracer, and if you look dynamically, this is what's happening. All right, so I'm now going to speculate about the mechanism here. So this has been observed in observations to some extent. There was a substantial observational program back in the late 2000s, early teens, called the Hawaiian Ocean Mixing Experiment, or HOME, in exactly this area. So here's that line going across the Kauai Channel. And these are the beams that were calculated with non-linear stratification. And here is an example of the density field. And you can see in the vicinity of the beams, the density field has an elevated structure. So they have kind of observed this back in the period of the HOME experiment. And back in 2009, they argued that the momentum flux divergence corresponded to weak flows. So the momentum flux divergence meant some sort of transport into the center here and then leading to a vertical motion. They found they tried to quantify it, and they found it to be a weak effect, smaller than what's needed, but certainly in the correct direction for the transport. All right, so I'm going to draw on Stokes drift to explain this. And I'm going to say this is speculation. We haven't proven this, and I don't think it's actually very clear from the PO literature exactly what's causing it. But I'm going to remind you about Stokes drift. So Stokes drift, everyone? That's okay? Thank you. So anyway, Stokes drift is the result of a change in the transport on one phase of the orbital cycle relative to the other phase. And we're familiar with it with surface gravity waves. Because there's a vertical gradient in the orbital structure, there's a difference between the transport in the direction of the phase propagation at the top of the wave versus at the bottom. And that leads to a net transport. All right. This comes from a textbook on internal waves by Bruce Sutherland, who's one of the experts of internal wave theory. And in this formulation, the Lagrangian transport is basically proportional to the amplitude of the internal wave squared. And it's related to the horizontal wave number and the stratification, of course, and the frequency. It can be expressed this way as well, where theta is the angle of the phase propagation relative to the horizontal. And because of this, there's a Lagrangian transport associated with internal waves. So if we think about that first beam coming up, the beam has an angle with the vertical. The phase propagation shown here has an angle with the horizontal theta. And the horizontal wave number is negative, and that leads to a negative Lagrangian transport. So what's important is that the beam has a very significant structure in the amplitude squared. So it's largest in the center of the beam, and then it moves off to a period where it's got 0 amplitude before reversing on the other side. And so there's going to be a Lagrangian transport to the side of the beam associated with this process. I'd like to say I'm 100% sure that this is correct, but I am not 100% sure, and we're still actually looking at it to try to prove this. All right, I'd like to move to a second topic. So this relates to realistic simulations. So here is a simulation that I like to show. It shows the California current in the regional ocean modeling system. It shows all of the beauty of the California current with seasonal variations in the temperature, moving to summer now and winter when the surface temperature gets blue. You can see all of the mesoscale structure and submesoscale features that are quite common in our area. During summertime, you can also see the filaments of cold water associated with coastal upwelling. So we all understand that story very well, but the goal is to try to constrain these models using data. The reason we want to do that is because they're nonlinear coupled differential equations. There is a lot of uncertainty that's associated with them in all sorts of ways. So we have uncertainties in initial conditions. We have uncertainties in surface fluxes, uncertainties in boundary conditions. We have uncertainties in discretization. Using discretization leads to different levels of resolution of processes. There are uncertainties in the unresolved processes that we'll never get down to, the mixing in particular. There are uncertainties in numerical schemes that are used, and then choices of modeling. Just to point out a couple of these things, as oceanographers, I'll just say me, we often think that the atmospheric modeling is perfect. And that's far from true. So here's this very nice analysis from Raphael Dussin in 2016, where they're looking at the ERA interim product. This is from ECMWF. It's a very, very high quality product from one of the world's best atmospheric modeling teams. And they show a substantial spatially coherent structural bias this is just in the shortwave radiation field. And this is because of the very difficult problem that's associated with representing clouds in atmospheric models. So I kind of like this because it shows really an enormous bias in the California current. One might argue that this can be addressed by applying a multiplicative factor that's as large as 15% reduction in the solar radiation in the eastern subtropical Pacific. It's not quite as simple as that because this has effects also on the long wave radiation, which is outgoing, so those are competing effects. My point in simply showing this is that at the start of what forces an ocean model, you have to start thinking about errors. If we add biogeochemistry, there are enormous sources of errors there, and I talked about the Frank's model before, actually a slight adaptation of this with a detrital component. This is a nice simple model. We do a lot of work with the Nemero model, which is shown here with multiple 2 phytoplankton, 2 zooplankton, so it's not that much more complex than this, but it's got silicate and nitrate as well, so 2 macronutrients. But of course, you can go up from there. This is a nice one out of Australia, the E-Reefs model, and this has a state vector length of 130. So 130 elements that are very poorly observed in the ocean. So anyway, there's a lot of uncertainty that starts with the atmosphere. It goes through the physics, which I'm skipping over largely here. And then even on the biogeochemistry, we have uncertainty in the model formulation and then observing it. Parameter choice matters a lot. So here, I'm just going to describe the Frank's model. Here's that primary production that we talked about before. You've got grazing that's represented as what's called an Ivlev formulation, and then a linear mortality. Very simple model, but this model has 9 unknown parameters. And the laboratory experiments don't measure exactly these parameters, but perhaps we can find them from laboratory experiments. But because they're coupled nonlinear ODEs, they exhibit very complex behavior. I like this figure back from my postdoc days because it shows that even a simple model which looks stable, so this is showing the time evolution of the different fields set up in a simple one-dimensional context. At some depths, you have a stable system, but at other depths, because of the change in the light level, you can get oscillations, which are very common in these sorts of predator-prey type models. And the timescales for those oscillations are dependent, of course, on the parameters or on the fields like the light level. So you can go from a stable situation at the surface to a stable situation at depth, but passing through periods of instability in between. And you can do complex analysis in parameter space, which shows how diffusion impacts these things. In some places, it couples processes at different depths and leads to stability, but dependent on other parameters, you might find regions of instability for the whole water column. All right, so how do we deal with these? We can do parameter estimation problems, and this is work that Paul Matern did a few years ago. This is using that NEMRO model, which is a model of, I'll say, intermediate complexity. You can run Monte Carlo simulations where you vary the parameters within known, within reasonable ranges, say a factor of 2 or a factor of 10 of what you think they are. And you can run a very large number of these and minimize a cost function that is dependent on what few observations you have. What I'm trying to show in this plot is that here we ran 200 simulations, and I'm showing a cost function up at the surface relative to different parts of the observational field. Cost function simply means like squared deviations between a model prediction and observations that you have. And for some parameters, you had a very large cost function, which meant the agreement was very poor. That's shown on the right here. But for some parameters, and we highlight 10, you have actually pretty uniform overall model response. And that's difficult to deal with because you basically have correlations in the impact of different parameters in a model. So if you increase the growth rate, that's kind of like decreasing the grazing rate. They work in opposite directions. And so what I'm showing here is either an increase from our reference parameter set or a decrease. Let's see, blue, I think, is a decrease, and red is an increase from our reference. But it actually might be the reverse, sorry. Anyway, my point in showing this is that as the number of parameters grows, it's very hard to optimize the parameters in a unique way. So this is one important way to do biogeochemical model tuning. It's not the only way. A different approach, but similar, is to use a more complicated machine learning algorithm. Oh, actually, I'm not showing the machine learning algorithm in this result. I'm showing the ensemble actually same as before. So observations, for example, in the area average is shown on the left. This is surface chlorophyll. Our reference simulation is shown here, and then a best in ensemble is shown over on the right. The error is shown as the right panel, and you can see by optimizing on this cost function, you can improve things, but you don't get to zero error. All right. A different way of handling this is through data assimilation. So data assimilation is a rigorous method that's used in atmospheric and ocean sciences. And I like to present it as it's similar to fitting a line. Many of you have fit a line perhaps in the data analysis class. A few people. It's a good thing to do. So here we've got data points that are shown with equal uncertainty, 10 data points. And I'm sure in your exercises you fit those data points. Did you fit them with equal uncertainty or weighted errors where the different points had different errors? Did you remember? It's all right if you don't remember. All right. What the figure on the bottom right is showing is that you can get very different line fits depending on what you know is the uncertainty in different points. This is kind of obvious, but I'm just going to point it out. So the blue line here assumes constant error with all of your data points shown as the red dots. These two lines, the dashed red one and the dashed black one, assume very low uncertainty in this first data point. And so the line that you get should reflect that. It should pass through or close to the points with low uncertainty. So the black one had low uncertainty for 0.1 and 0.7, I think. That's this one here. So if you have very low uncertainty for 2 points, those are going to be upweighted in the line fit. And my point is that uncertainty in the observations makes a really big impact. So fitting a line is straightforward. This is an overdetermined problem. We have two parameters, A and B, that we're trying to fit, but we have 10 points. And if we know something about the uncertainty, we can get a good estimate of those values. In the data assimilation problem in the ocean, instead of having 2 parameters, we might have 10 million parameters. And we don't have 10 million or 100 million observations. So it's an underdetermined problem instead of an overdetermined problem, but the principle is the same. Okay, so here the type of data assimilation that we do is called 4-dimensional variational assimilation. And we call it that because it happens in 4D space, 3 space dimensions and 1 time dimension. And I like this schematic up here, which kind of shows what we're doing. So you have some prior estimate. You predict the weather for today or tomorrow. And then today or tomorrow happen, and a number of platforms collect observations. They might be Argo floats, satellite observations. They might be shipboard observations by Calcoffee or nymphs, or maybe they're exotic observations from novel platforms. Anyway, the data comes in, and you can see deviations between the estimate that we had initially and the data that came in. And so you can adjust control vectors. You can control certain aspects of this, like the forcing or the initial conditions, to produce a final analysis, shown as the blue line here, that is hopefully closer to the data that comes in than the prior estimate was. It's called 4D in time because it allows data to come in spread out over time, where we use ocean dynamics, like the Navier-Stokes equations, to basically connect a temperature observation at this time with what must have been happening 3 days before. A demonstration of that for temperature, sea surface temperature, is shown on the bottom here, where we have an original model field. That's our model estimate. That's our prior. And then satellite data comes in. Lo and behold, certain regions are colder than other regions. And so we put these things together to get a final estimate that has a lot of similarity to the original model field. It's unchanged, particularly in places where we have no data. But in places where we have a large discrepancy between the prior and the observations, we can adjust those model conditions to produce colder water in this area. Anyway, this is the principle of 4D VAR. Okay, here are the observations that are useful to assimilate. In the physical world, we've got satellite data, we've got sea surface elevation, sea surface temperature. We've got gliders that are out along the whole west coast, which are fantastic. We've got the Argo floats, which are throughout this area. We've got HF radar, and we've got shipboard measurements that happen infrequently but are very useful. All right, we assimilate this data and produce state estimates for the physical ocean state that go back to 1980. And we serve those on a UCSC webpage. These are then taken up by various people. Have any of you heard of the Bakken Index? Okay. Beauty and Cutie? Okay. So Beauty and Cutie actually come from this data assimilative product. I don't know if you know that. It accounts for the onshore geostrophic flow that is associated with coastal variations and the wind stress that takes place. The alongshore wind stress is not uniform from Point Conception up to Cape Mendocino, and as a result, there are differences in sea level that are associated with that, and you get onshore geostrophic flow. And the QD index, Coastal Upwelling Transport Index, can account for that using this data assimilative model. And then the beauty one is a biogeochemical one by not assimilating biology, but taking a statistical relationship between density and nitrate and linking it with the upwelling that has to be taking place 40 or 50 meters below the surface, and then coming up with a nitrate transport that's associated with that. Anyway, that is dependent on the type of assimilation that we produce. All right, so a lot of the 4D VAR procedures have been developed for the physics, and a lot of my work has been to try to extend that into the biogeochemical world. This is a figure that I often show to demonstrate its utility. This is kind of nice because it shows how little data we have, and it also shows the impact of the assimilation. So what I'm showing at the top here is observations. This is 1 year of surface chlorophyll, both in the time mean and in the Hofmüller diagram as a function of latitude. So this is near the coast, inner 100 meters. And you can see about 30% of the time there's no data because of cloud cover. But you can see hotspots at a few of the points along the coast, near Point Conception, Point Reyes, up off of Cape Mendocino. A model with no assimilation gets some of this right, but a lot of it wrong. And then by assimilating that chlorophyll, we can produce an estimate that is much closer to the observations than would occur in the absence. But it highlights how little data we have. So when we started this work 10 years ago, we really only had satellite chlorophyll. Today, we're in a really exciting world where new data types are coming online. What are the in situ data types for biology or chemistry that you're familiar with? Anyone hear the SUNA device, which is on gliders? So this is a nitrate sensor, which is now on gliders. And just down the road, Yui Takeshita is one of the people who has developed this fantastic pH sensor that's now on gliders as well. So this was the most recent work that we're doing on this. It's nearly, our first paper on it is nearly submitted. Here's an example in January 2023 of all of the observations in the California current that were biologically relevant. So you can see a lot of floats that are out there, gliders, there are some nearshore stations. It's pretty sparse, but we now have oxygen, we have pH, we have, in some cases, nitrate, but we can also use these global statistical relations that have been developed by Brendan Carter and colleagues up at PMEL in the Pacific Northwest at the PMEL lab in Seattle. And these show very good agreement from the GLODAP database between physical properties, temperature, salinity, and location, and predicted nitrate, silicate, phosphate, pH, total alkalinity, and so on. So we've adapted our model to handle the carbonate system. We've added oxygen, alkalinity, calcium carbonate, DIC, pH, and PCO2 to our more traditional model, and built adjoint and tangent linear models that are necessary to do the 4D VAR. Our first foray into this was difficult. We tried just assimilating the pH alone, and that's what's shown in the left panel. So here are our prior estimates. Here's the data coming back in black, and here was our posterior. And the issue here is that the carbonate system needs two components. You probably know this much better than I do. You need total alkalinity and DIC, or you need pH and total alkalinity to predict the third. And we were moving to the right pH, but with the wrong DIC. So we have to use the statistical models along with the observed data to come up with estimates that are consistent with the observations. That was a discovery on our part. All right, we have an experiment in 2019 where we're assimilating a lot of data, and I'll just skip to kind of the results. This is what happens when we assimilate data. You can see very clearly the instantaneous adjustments are where the data is along the glider. But because the ocean circulates, you end up getting changes over the course of a year throughout a large area of the domain. And we don't actually know if these are improvements. We don't have that much data to evaluate it against, but here we do have data that we can compare it to. So this is simply showing that along a glider transect going off of the Monterey Bay, if we have observations of pH, they look like this. The free simulation looks something like this, with a difference shown on the right. And if we do assimilation without local observations of pH, we get results that are worse than the simulation. But if we add the observed pH and the estimated alkalinity, we can get quite a bit better estimates of the pH in this region, and we believe that those spread to the rest of the California current system. So this is all actually quite recent and exciting. What it means is that as the gliders get the pH sensor, and we'll have them up and down the coast, we'll be able to be looking at ocean acidification in a state estimate sort of way up and down the coast. All right, so the work that I do involves process studies and realistic models. I really like to work particularly with students on process studies where we look at basic interactions and try to look at the physics effect on the biogeochemistry. Realistic models are fantastic, but they have a lot of errors that are associated with them in every part of their, every step of their process. We can constrain those errors through parameter optimization, and that's very useful. But it doesn't get us all the way there. In addition, 4D-VAR or other methods of data assimilation are useful to constrain the models and get them really close to the observations. We're doing this both with the physics and with the biogeochemistry, and as new data types come up, we really like to develop methods to take advantage of them. We've gone from one biogeochemical tracer now to, if we add these statistical estimates, to more than half a dozen. So it's really exciting. Thank you very much.
Forcings and if that was taking into consideration any El Nino or ENSO events, and if you guys will potentially look at that in the future.
Are you asking if we look at uncertainty associated with predicting ENSO events, or are you thinking about as the ENSO event comes through the California current, if we try to look at the impacts of that?
Yeah, and how it affects both the biogeochemical.
We do. I didn't talk about it, but actually we do. We have looked at, so we have historical analyses that go back to 1980, and from those we can analyze the density structure changes that take place in the California current as the ENSO event makes its way off of our coast. It suppresses, as you know, it suppresses upwelling off of the coast, and we can analyze that in the model. In fact, when the 2016 El Nino was coming through, 2017, I think, El Nino was coming through, Mike Jaycox made a prediction of the impact to upwelling, a 3-month prediction based on historical analysis of the historical model output with expectations of the strength of the event based on the equatorial ENSO indices.
Cool. Thank you.
Hey, I have a question about when you're assimilating your models with your observed data. Is there like some sort of threshold where you kind of start questioning your model if it passes like if they're too far apart?
Yeah, that's a great question. So we do the same sort of error analysis that you do probably in your class. So the model has uncertainty, and specifying that is a whole topic that actually mostly just data assimilative modelers care about. It usually puts people to sleep, but we do have estimates of uncertainty for our model fields, and so we assign them in the formal assimilation process. So we've got a model uncertainty. The observations also have uncertainty. They have an uncertainty that's instrument uncertainty. They also have what's called error of representation, where the instrument is located at a point, but our model grid represents a spatial average. And so we try to also incorporate the uncertainty of the relationship between a point measurement and its own variability within, say, let's say a 1 kilometer by 1 kilometer box or something like that. And then we square those and add them following an error propagation formula. And then if we assume that the errors are Gaussian, we might assume that it's very unlikely to have discrepancies between our model and the data that's more than 3 sigma from 0. And so when we find, we have a threshold of basically 3 sigma, and when we find observations that are outside of that relative to our model prediction, we throw them out, not because the data is wrong, but because they're so inconsistent with our model that, that we can't tell. Is it the data? Is it the model? If we have, it's actually very few data points that get thrown out, but we do have a procedure for handling that.
Thank you for your talk. And I also had a question about the data assimilation. So after you assimilate the data, you mentioned how it kind of like, you can check how it improves like compared to the original model to the observed. Does assimilating data help with future predictions of the model?
Yeah, I didn't show any of that either, so thanks for asking that. We can look at, so when we do this, I want to say most of my work looks backwards. There's so much work that is making climate projections, and I'm loosely involved in those, but it doesn't really involve data assimilation. So if you look back and you have a long record, you can actually you can make a data assimilative estimate for one day, and then you can make a prediction from that into the future, and you have a lot of observations that you can compare to. So we do those sorts of analyses where we run it into the future and we see how long before we get a large error. And the answer to that actually depends on whether we're talking physics or biogeochemistry. The physics actually loses its memory fairly quickly. And that, as a result, we assimilate only over kind of a week time scale. And we find forecasts are good for a week, 2 weeks. And then we get into less certainty. Anyone who does forecasting knows there's kind of a valley of death around seasonal forecasting, sub-seasonal forecasting. And then, of course, things get better on a climate scale when the trends exceed the variability. Anyway, so there are periods that we feel like we have good predictions. It turns out on the biogeochemistry, we actually have much longer predictive skill out, I'll say, order a month or a month and a half rather than a week or so. So we do think about that, and we, well, we're actually quite happy when it is a long, has good skill out on that time scale.
All right, thanks, Chris. You showed a couple nice comparisons with the modeled chlorophyll A and the remotely sensed chlorophyll A. But of course, the remotely sensed chlorophyll A is going to come from some integral of some depth. And so I'm wondering, when you do this comparison, what depths you do that over to get the modeled chlorophyll A values, and then how you choose that depth?
Yeah, fantastic question. Yes, so in this comparison, we fly fast and loose. This is what we're showing in this case, I'm 95% sure, is the surface chlorophyll concentration. We actually have some work where we are doing a radiative transfer calculation in the proper way with the idea that we can assimilate that product, basically an RRS, which is what the satellite is reporting, and not a surface chlorophyll product. But that work has not yet yielded good fruition. So we are assimilating into the surface layer. We're assimilating the data in the surface layer, but the high mixing in the surface mix layer means that we're really having it represent the upper 20 meters, depending on time and where you are here in the California current.
I think we have time for one more.
I just had also another question kind of related to depth. When you're talking about the glider, is it at a constant depth, or is it changing in depth as it goes?
Great. So this is showing the observations. These are the glider observations, and this is longitude up here. So it's kind of strange, but it starts at Mbari here, and then it goes offshore, and then it comes back to the shore. And all along that, it's oscillating at very very high density. And this is the model interpolated to exactly the glider positions in time.
Well, I think that's it. If anybody has any remaining questions, I think Chris will stick around for a little bit, and let's give him a final hand.